In the name of Allah, the most beneficent and most merciful. You know, in this chapter of unsteady flow, previously what we have discussed, how to compute emptying time for a tank, water tank, overhead tank, reservoir. And in that case, we have discussed two cases of the water overhead tanks. One is the cylindrical tanks and other are the conical tanks. So you are in a position to compute emptying time for both type of tanks, those if those are cylindrical or if those are conical. In case of cylindrical tanks, so the area, surface area of the tank that we cannot write in terms of H, which is the head, but the Q2 we have to write in terms of H. But in case of conical tanks, the surface area also changes with change in head. So that's why we have to write both the surface area in terms of H and also the Q2 in terms of H. And once we have these two equations, then we can simply integrate from H1 to H2 and then we can solve the problem. Now today we want to discuss a similar problem but flow over weirs and under varying head. So this is a weir, you know. Where is, yeah, this is pointer. So here there is a weir and you know what is H? We very well we know about the H. H is the head over the, what is H exactly? Yes, crest of the weir. And this in the discharge measurement chapter, we discuss in detail a broad crested weir, short crested weir, etc. So it's a function of the H. And you know, so this H, again, it depends if the Q1 and Q1 is the inflow to the reservoir, like Tarbela Reservoir, Mangla Reservoir, and this is the dam and the spillway, and this is the Q2. Which is the outflow from the reservoir. Outflow from the reservoir takes place over the spillway, or it may sometime take place from the under sluices. It may take place from the power tunnels, which supply water to the turbines. Here we are just considering over the spillway, okay? And you know, when this Q1 and Q2 both they are equal, then the flow over this spillway would be steady or unsteady.
Steady, sir.
Steady.
Then it would be steady. But when Q1 is not equal to Q2, in that case, flow over the spillway will become unsteady. Okay, and those problems we want to solve. In case of unsteady flows, or if the Q1 is 0 and if there is only Q2, so this H over the crest of the weir will be keep on decreasing. So in that case, how to compute the emptying time for this reservoir, or to bring the level of this tank to here, okay? So the same is mentioned here. Figure shows flow over a spillway or weir from a reservoir. Of surface area, capital A is the surface area of the reservoir, and varying head small h. Reservoir receives an inflow Q1 and outflow Q2. Now, how we can solve this problem? We can apply the continuity equation between section 1 and section 2. So we know that the Q1 minus Q2 should be equal to change in storage with respect to time. And where ds over dt is the change in storage. Storage means volume. So this ds over dt, we know that this is also equal to area times dh over dt. So dh over dt is the rate of change of depth or change of head over the weir with respect to time. And we know that the Q2, which is the outflow from the weir, it has this weir formula, CD 2/3 root of 2g BH plus V square over 2g, its power 1.5. And this formula we have already discussed in detail in the discharge measurement chapter. or this is the same equation. What we have done here, the velocity of approach, which is very, very small. So we are neglecting that. And so h plus that, we are only saying that h has this much power. And then writing the same equation 1 and 2 and putting values, you will get this equation for dt like that, and t emptying time for reservoir up to certain level from h1 to h2, that we can obtain by integrating this above expression and a q1 minus q2 into dh. And here you see this is the same equation which we derived for the overhead tanks, that the emptying time is integral h1 h2 area over q1 minus q2 into dh. But only we have to put the value of the q2. And what is the q1? Q1 is the flow which is coming from upstream in the reservoir. And q2 basically is a function of small h. So if we know the h, we can compute the q2 like this. So this is the governing equation to compute emptying time, to lower down the water reservoir level from any to when the h, if you want to any value of the h. Okay. So this is how you can compute the emptying time for reservoir. And with this, we have finished this topic. If you have any question, you are welcome. Now, this was the case of open channel flow. Previously, we have discussed the overhead tanks, and there were orifices. And in case of orifices, the flow in the orifice, over it, there was certain pressure. Is that okay?
Sir, area h का function होगा head का?
Yes, actually area would be, of course, function of h in that case. If this h is significant, then of course as the h will reduce, the surface area will also reduce. And we can develop relationships between the surface area and h. When h is 0, tabhi koi surface area hai. This and like that, there is certain surface area. Anyway, my point is that we have a very same equation to compute the emptying time. Only Q2 की जो value है, that would be now the equation of the discharge over the weir. We move ahead.
Yes, sir.
Okay, now we want to discuss another topic, which is the water hammer or hammer blow. That is same thing. Now to understand this water hammer, we have to consider this is the model of a reservoir. And you can see that this reservoir, practical examples are Tarbela Reservoir, Mangla Reservoir, Chashma, any reservoir. And then this is a pipeline of length L. And here there is a valve. Okay. So this practical example of this pipeline could be penstock, through which we supply water to the turbine under pressure. And here there is a valve, and we already discussed that. What is the practical example of valves in case of hydropower plants?
Yes. So spare
to increase or decrease the discharge.
In case of impulse turbines, that is a spearhead needle, and in case of reaction turbine,
governor, sir.
Those are movable guide plates. The function of governor is different. Function of governor is to keep the RPM of the turbine shaft same, equal to the normal speed of the turbine. Even the load on the turbines, they change. Okay, that is the function of the governor. So now, so it depends that how do we close this valve. If this valve is suddenly closed, then you know what is going to happen. Here, very high dynamic pressure will develop. And do you think that it will only develop here? Then this pressure wave, it will move in this direction. All right. And
yes, sir.
When this pressure wave will move in this direction, let's say its diameter is capital D, then due to that very high pressure, and if this pipe material is elastic, then what will happen to the diameter? Would it remain same?
Increase, sir. So it will increase, sir.
That will slightly increase due to elastic action. And you know, each material has certain elastic limit. And you know, this we will discuss in detail as given here. Whenever velocity in a pipeline is reduced instantaneously, when we very closely we close this valve, very rapidly we close this valve, or in a very short time. What is instantaneous closure? We are taking very less time to close the valve. A sudden increase in pressure takes place here. This sudden rise in pressure in a pipeline due to stoppage of flow is known as water hammer or hammer blow. So here the pressure will increase a lot. The increase in pressure is so high that the pipe may burst. So this pipe, which is the penstock practically, and it is not strong enough to withstand that pressure if we have not designed that penstock properly to take care of that water hammer pressure. So water hammer pressure is not a usual pressure, it is more than that. So water hammer is used for all type of fluids. It is not specific to water. इसका नाम क्या है? Water hammer. But does not mean that if, for example, if in some mechanical machine, if the same thing we are doing, we are stopping a valve and there is mobile oil or any other liquid is inside, again the will call that is the water hammer. But you know, in case of widely the liquid used is of course water, particularly in the hydropower plants. So why there is water hammer pressure? The water hammer pressure. Sorry?
That is water hammer से हम find क्या करना चाहते हैं?
Yes, very good question. What we want to find? We want to find that how much the dynamic pressure. Okay, wait. Suppose if this height is h, यहाँ से लेकर यहाँ तक, है ना? Yeah, if I draw a line horizontally like that, and if this height is h, and if this valve is closed, you know, in normal conditions, very slowly we have closed this valve, and here the velocity has become 0. So please let me know how much would be the pressure head at this point. कितना pressure head होगा? ये जहाँ पे अभी वो पड़ा हुआ है pointer.
H, sir.
H would be the head. Okay. At this point, how much would be the head? If the valve is closed, valve is already closed. Maybe एक दिन से बंद है valve, है ना?
Same होगा.
कितना होगा?
Same. H, sir.
H? Are you sure?
Yes, sir.
Yes. The pressure would be same H. Pressure head. And how much would be the pressure here? Gamma times this H. Okay. But when I will close this valve instantaneously. Oh, okay, one more thing. Suppose if this valve is open and the liquid is flowing in this pipe, then how much would be the pressure head here? Would be equal to this much head, है ना? लेकिन यहाँ पे कितना होगा? So this would be the hydraulic trade line. नहीं, थोड़ा सा अंदर कुछ तो होगा ना?
Yes sir.
Yes sir.
Of course यहाँ आके बाहर 0 हो जाएगा, ठीक है ना? तो so it means when we close this valve suddenly, then a very high dynamic pressure will develop. अगर मैं ये valve वैसे बंद रखता हूँ तो pressure head कितना है? Equal to H. मतलब अगर कल से 2-3 दिन से बंद है, and in that case this head would be H. But if I suddenly close this valve, तो ये जो dynamic pressure head है, that would be total pressure head would be more than that. Okay. Now this pressure head is called as water hammer pressure, which can burst this pipe. So what is our main, as your question is, why we are studying this, what we want to compute? We want to compute that dynamic pressure, which will produce due to closing of this valve. Is it okay?
सर ज्यादा क्यों होगा ये? वेलोसिटी कन्वर्ट हो रही है ना हेड में.
जी वो I think you should wait for maybe 15 minutes. Then you please again ask me the same question, okay? Because we have to discuss something else. Then please don't forget to ask me, huh? All right. Sir. Now, why this water hammer pressure will generate in the pipe due to inertial head? You know that inertial head. The liquid was flowing. उसको आपने बंद कर दिया है ना? तो and that can be expressed by Newton's equation. Let V be brought to 0 in time t. Then what is F is equal to m times A. This we know very well. So what is the force F? This Pi, which is the initial pressure. Sorry, not initial, inertial pressure into the A. A is the area of pipe. So this is equal to m times A. This is the mass, rho A into L. L is the length of pipe, A is the area. So this is the volume of pipe into rho is the mass into V over T. This is the acceleration. So if you will solve this, Pi is equal to gamma VL over GT. So this is the inertial pressure. So it means this inertial pressure which will develop due to instantaneously closing the valve is proportional to 1 over T. If we take more time to close the valve, what is T? T is the valve closing time. So if this T, we are taking a very long time to close the valve, then the pressure developed would be higher or lower?
Lower, sir.
Lower.
But on the other hand, if this time taken is very less, then the inertial pressure which will generate in the pipe is very high. Suppose, theoretically speaking, if this time taken to close the valve is 0, then what would be the initial pressure in the pipe which will generate?
Infinite, sir.
Infinity.
It is infinity. Okay. But you know, practically this time t, we cannot make it 0. Practically some time will be taken to close the valve. Anyway, here I want to just explain that this initial pressure, inertial pressure which will develop in the pipe due to closing of the valve is a function of 1 over T. So then what would be the pressure head? We know the pressure head simply divided by gamma. तो वो हमने gamma से divide कर दिया. So once you will divide the gamma, the equation for the inertial pressure head, that is VL over GT. And if t is equal to 0, which is not possible as we have already discussed, the HI would be infinity. So the pressure and pressure head given in equation 1 and 2 do not approach to infinity practically because, as we discussed, it has 3 reasons why it does not approach to infinity. It is difficult to close valve in 0 time. The first thing is that. The second, water behaves as compressible fluid at higher pressures. At very high pressure, water itself gets compressed. And number 3, material of pipe behave elastically up to certain limit. That also expands. So these are the 3 reasons. Okay, now here the concept of water hammer pressure is shown in this diagram, and this is a reservoir, maybe like Mangala Reservoir or Tarbela Reservoir. This is the model of it. This is a pipeline like the penstock. This is a valve which we have to close, and V is the velocity of flow in the pipe, at normal conditions when this valve is open. And let's say the starting point of the pipe is M. You can say this point at a certain distance is B. This is the section B, and this is the N is basically the location of the valve in the pipe. So this is the normal hydraulic grade line. Is it okay, bhai? The normal hydraulic grade line है, which gives us the pressure head. So it is like that. And when this valve is slightly open, and this is the transient hydraulic grade line. Transient means जो instantaneous change हो रहा है due to closing of this valve. And this is the pH over gamma. What is pH over gamma? This head. This head is the hammer pressure head. pH is the hammer pressure, our inertial pressure, and pH over gamma is this water hammer pressure head. So now you can understand that due to this closure of valve, this much pressure that will increase in the pipeline. And what happens? The laminas of the fluid, once this valve is closed instantaneously, so these laminas and the pressure wave will move in the upward direction with the velocity of Cp, celerity velocity, and that we want to discuss in the next slides. Let x is the distance from entrance to this pipe up to certain section B. Is this length of the pipe is x, and as the total length of the pipe is capital L, so the remaining length of the pipe is L minus x. Is it clear, the things up to here?
Yes, sir.
Okay. Now we want to discuss in detail the water hammer phenomena or the process. What happens once we close instantaneously the valve of a pipeline? Now the A, normal steady flow is taking place. ये कब होगा? When the valve is closed or open? When the valve is fully open. The pressure throughout the pipe is normal. तो जो pressure इसमें होगा वो normal pressure होगा, and the pressure head would be P over gamma. Now the valve is closed instantaneously. What will happen now? The laminas of the liquid are compressed against the valve. A pressure rise takes place, which begins to travel upstream with a velocity of Cp. Cp velocity से वो आगे जाएगी pressure wave. After time t, which is equal to L over Cp, the pressure wave has traveled the entire length of the pipe, making pressure high and stretching the entire length of the pipe. So now this we have valve closed. So the pressure wave, positive pressure wave is now moving in this direction, which will stretch the diameter of the pipe. Okay, and how much it will take time from this point N to reach to point M. If L is the length and Cp is the velocity of the pressure wave, so L over Cp would be the time to move the pressure wave from point N to M. Is that fine? तो ये समझ आ गई? Now we are trying to understand. We are trying to understand what happens when a valve is instantaneously closed. वो हम समझना चाह रहे हैं होता क्या है. अच्छा जी, now what is the point C? Now the compressed air, compressed laminas, ये जो of liquid begin to relax back. In the first, when you will close the valve, a positive pressure wave will move in this direction and it will take how much time? L over Cp to reach M. Now the same will come back and now the pressure will become the normal and it will come back to the point N. How much time it will take?
T, sir.
There is pressure wave Cp.
V over L.
Now again the time taken would be L over Cp to reach here. It means after a time 2L over Cp, how much would be the pressure here at point N? कितना हो जाएगा? Normal. Yes, normal. जो पहले था, है ना? So this till now we have discussed this thing. Now we have to discuss the point C हम कर चुके हैं, है ना? ये the compressed laminas of liquid began to relax. अब relax होंगे. And a wave of unloading begins to travel from M to N. So this is point N, this was point N. Pressure throughout the pipe becomes normal. In time L over Cp on point N. Now again what will happen? At the same time, the जो last lamina है, against the valve moves back and a negative pressure is created in the pipeline at the valve, which is theoretically of the same magnitude as of the positive pressure. So this negative pressure travels with a wave of rarefaction, negative pressure wave, with making pressure negative in entire length in how much time? T L over Cp. Now a negative pressure wave will move in this direction from N to M. And when it will reach to point M in time L over Cp. When a negative pressure wave will move, what it will do with the pipe material? It will try to reduce the diameter slightly of the pipe. Okay. Now what will happen further? Now the
negative pressure आता क्यों है?
Negative pressure that comes basically due to dynamic effect. ठीक है ना? And the wave of negative pressure return back from M as a wave of normal pressure. अब फिर ये negative pressure फिर normal हो रहा है. And the pressure becomes normal in the entire length in time how much? L over C. Okay? Yes.
जो वाटर में वेव्स होती हैं तो लॉन्गिट्यूडनल वेव्स नहीं होती, तो उसमें रेयरफेक्शन कैसे आएगा? क्योंकि लेकिन अगर अलोंग द एक्सिस वो मूव करेगा, वाटर ट्रांसवर्स मूव नहीं करेगा, तो या तो कंप्रेस होगा या एक्सपेंड होगा.
नहीं, ट्रांसफर तो मूव कर ही नहीं रहा, मूव इसी डायरेक्शन में कर रहा है, बट द प्रेशर बिकम्स नेगेटिव. ठीक है ना? जो प्रेशर वेव है, पॉजिटिव प्रेशर वेव एंड नेगेटिव प्रेशर वेव, दे आर मूविंग अलोंग द लेंथ ऑफ पाइप.
Yes, sir.
Now the main thing is the above sequence continuous, and practically the intensity of pressure keeps on decreasing due to frictional and damping effects. And after some time, pressure becomes normal in the pipe. This happens when we close a valve instantaneously. Okay, now we again I would like to summarize again here on this diagram. So this is the reservoir, this is a pipeline, and if this valve is instantaneously closed, initially what will happen? A wave of positive pressure will move in the upstream direction and will reach here. So it will stretch the pipe hole and will slightly increase the pipe diameter, and the time taken would be L over Cp when it will reach from point N to M. Then the unloading pressure wave, पहली थी loading pressure wave, positive pressure wave, अब है unloading pressure wave, will move from point M to N, and it will take a time of L over Cp, and due to which the pressure will become normal in the pipeline. Then the thirdly, what will happen? Now there would be a loading of negative pressure wave, which will move with a velocity of the Cp and will reach here at a time of L over Cp at point M. And due to this negative pressure, so the diameter of the pipe will slightly reduce due to elastic action. And then finally there would be unloading of negative pressure wave, and the pressure in the pipe will become normal, and at point N, this unloading negative pressure wave will take a time, how much? L over Cp. So this is the one cycle of the water hammer pressure, and then it will keep on occurring, and there will be damping and reduction of these pressures, and after some time the pressure in the pipeline becomes normal. This is the water hammer phenomena. Okay, समझ आ गई जी?
सर नेगेटिव प्रेशर जो होगा वो एटमॉस्फेरिक प्रेशर से कम होगा, इसलिए हम कह रहे हैं ये जो पहले हेड है उससे कम होगा नेगेटिव प्रेशर सर।
नहीं, नेगेटिव प्रेशर का मतलब ये है कि वो जो पहले प्रेशर था उससे कम हो जाएगा। नेगेटिव प्रेशर मींस प्रेशर कम हो गया है, ठीक है?
यस सर।
All right. Now the same thing which we have studied, that if we will sketch the theoretical water hammer pressure distribution diagrams with time, तो वो हमें सारे point clear हो जाएंगे. Water hammer phenomena will further clarify. Now this is a reservoir and this is a pipeline, and this is point M, point B, point N. L is the total length of the pipe. Let's say the distance, the length of the pipe from point M to B is X, then this length would be L minus X. Is it okay? Now we want to first of all plot the water hammer pressure head distribution at point N. Point N कौन सा है? Which place it is? Point N. हाँ जी?
जिधर valve है.
जी, जहाँ valve लगा हुआ है. Now you see, once we will instantaneously close the valve, how much the pressure head will develop at the valve? So it will be pH over gamma. What is pH over gamma? Water hammer pressure head. This x-axis is time. How long this pressure will sustain at point N? यहाँ तक ये positive pressure कितनी देर तक रहेगा?
तो 2 साइकिल्स तक।
2 साइकिल, यस। देखें यहाँ से प्रेशर बढ़ा है तो ये अब ये आगे प्रेशर वेव आगे जा रही है, फिर ये जनाब जो क्या कहते हैं नॉर्मल प्रेशर हो रहा है, अनलोडिंग हो रही है प्रेशर वेव की, एंड यहाँ यहाँ पर जनाब 2L over Cp टाइम तक वही प्रेशर रहेगा एट पॉइंट N. देन व्हाट विल हैपन? उसके बाद लोडिंग ऑफ नेगेटिव pressure wave will start from here. वो चलेगी, वो चलती जाएगी यहाँ तक L over Cp टाइम, उसके बाद फिर वापस अनलोडिंग ऑफ नेगेटिव प्रेशर वेव होगी, इट विल टेक L over CP फर्दर टाइम। तो टोटल टाइम कितना हो गया? 2L over CP तक पॉइंट N पे नेगेटिव प्रेशर हेड रहेगा। ओके, ये कितना होगा? pH over gamma। अच्छा, द सेम साइकिल, ये तो दिस इज वन साइकिल है ना। उसके बाद अब क्या हुआ? अब जनाब फिर दूसरा साइकिल शुरू हुआ। फिर जनाब क्या यहाँ पे पॉजिटिव प्रेशर वेव, इट विल मूव इन दिस डायरेक्शन एंड देन इट विल कम बैक नॉर्मल होगी, अनलोडिंग एंड अनलोडिंग ऑफ पॉजिटिव प्रेशर वेव, इट विल टेक 2L over CP टाइम। उसके बाद क्या होगा? फिर प्रेशर यहाँ पे एक नेगेटिव वेव ऑफ प्रेशर वेव, इट विल मूव एंड देन इट विल कम बैक हियर। कितना टाइम लगेगा? 2L over CP। So this is the theoretical distribution of the water hammer pressure heads at any point at a point N with respect to time. Is it any do you have any question in this diagram? Shall we move ahead?
पॉजिटिव और नेगेटिव प्रेशर का मैग्नीट्यूड सेम है?
Yes, same है। This is same. Theoretically it is same. जो प्रेशर जितना पॉजिटिव प्रेशर डेवलप होता है, इट्स मैग्नीट्यूड इज सेम नेगेटिव होगा। नेगेटिव मींस सक्शन प्रेशर। अच्छा, this is the theoretical distributions of the water hammer pressures or pressure heads. प्रेशर और प्रेशर हेड में क्या फर्क है? ये हेड की फॉर्म में है, वो प्रेशर की फॉर्म में है ना। तो दिस इज द थ्योरेटिकल, बट व्हाट हैपेंस प्रैक्टिकली? प्रैक्टिकली अगर मैं लाइन लगाऊंगा तो वो यूं होगी, है ना भाई। आफ्टर टाइम 2L over CP पॉजिटिव प्रेशर भी कम हो जाएगा ड्यू टू डैम्पिंग इफेक्ट, ड्यू टू फ्रिक्शन। अच्छा, यहाँ पे ये नेगेटिव प्रेशर भी इतना डेवलप होगा, ये फर्दर कम होगा, लाइक दैट। इफ दिस नेगेटिव प्रेशर इज दिस मच, द पॉजिटिव प्रेशर वुड बी दिस मच, तो दैट विल इतना रह जाएगा। तो ये नेगेटिव प्रेशर भी इतना डेवलप होगा, इट विल फर्दर रिड्यूस। तो डैम्पिंग होते 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 क्या होगा? आफ्टर सर्टेन टाइम
जीरो हो जाएगा।
द pressure head in the pipe will become normal. Okay, now we want to draw this water hammer pressure distribution at point B. That is this one. Now consider this point B. मैंने valve close किया है. Once the valve is instantaneously closed, how much यहाँ पे pressure कितना होगा जब मैंने क्लोज किया यहाँ? तो हाउ मच वुड बी द प्रेशर हेड एट पॉइंट बी? इट शुड बी नॉर्मल, है ना। तो जनाब ये नॉर्मल प्रेशर होगा, कितने वक्त तक नॉर्मल रहेगा? यहाँ L - X over CP टाइम तक प्रेशर नॉर्मल रहेगा, उसके बाद एकदम बढ़ जाएगा एट पॉइंट बी, है ना।
यस सर।
अब नाउ द पॉजिटिव प्रेशर वेव इज मूविंग इन दिस डायरेक्शन and then unloading, there would be unloading of the positive pressure wave. So point B पर for how long the pressure head will remain pH over gamma? 2x over CP time तक pressure point B पे positive रहेगा। Okay, is it clear? ये जो positive unloading pressure wave है वो it is moving in this direction. And then negative pressure wave has to come forward with the same velocity. तो कितने टाइम तक नेगेटिव प्रेशर नहीं होगा at point B? Twice of L - X over CP. ओके, ये इतने तक पॉजिटिव प्रेशर जो कौन सा रहेगा? नॉर्मल। इज इट क्लियर?
यस सर।
अब प्रेशर कब शुरू होगा नेगेटिव? इस टाइम के बाद। तो नेगेटिव प्रेशर कितना होगा? थ्योरेटिकली इट हैज द सेम मैग्नीट्यूड ऑफ द पॉजिटिव प्रेशर, सो pH over gamma। अब कितनी देर तक यहाँ पर नेगेटिव प्रेशर रहेगा? सो एज द नेगेटिव प्रेशर wave has to move in this direction, then the normal pressure wave has to move in this direction. It means 2x over CP. So up to this time, the pressure head at this point would be this. And then you have to, it is one complete cycle, and then it is the repetition of the cycles. So at point B. Now we have to discuss the pressure head theoretical distribution of hammer pressure head at point M. Time कितना रह गया? अच्छा, this is the distribution of point M. When I will close this valve instantaneously, तो the wave of positive pressure head will move in this direction. तो जनाब कितने वक्त तक यहाँ प्रेशर नहीं होगा up to a distance of
L over CP.
L over CP. L over CP के बाद there will be instantaneous rise of the pressure head equal to pH over gamma, and for how long time? For theoretically 0 time, है ना? उसके बाद वापस प्रेशर नॉर्मल हो जाएगा, और वो कब तक नॉर्मल रहेगा? अब जनाब ये जो पॉजिटिव प्रेशर वेव की अनलोडिंग होगी यहाँ से यहाँ तक, फिर नेगेटिव प्रेशर वेव की लोडिंग होगी यहाँ से यहाँ तक, तो कितना टाइम लेगा? 2L over CP तक नॉर्मल प्रेशर रहेगा. उसके बाद फिर यहाँ पे प्रेशर कितना आ जाएगा? फॉर ए इंस्टेंटेनियस मोमेंट में यहाँ प्रेशर नेगेटिव होगा, एंड देन दीज साइकिल्स विल बी कीप ऑन मूविंग. ये एक इधर और एक इधर, लाइक दैट. So these theoretical distributions of the water hammer pressures are pressure heads. These helps us in understanding the water hammer phenomena in the pipelines. तो वाटर हैमर का ये नहीं मकसद है कि वेल क्लोज करें तो बस जी प्रेशर सडनली बढ़ जाता है, नहीं. पॉजिटिव प्रेशर वेव मूव करती है, फिर उसकी अनलोडिंग होती है, फिर नेगेटिव प्रेशर वेव मूव करती है, उसकी अनलोडिंग होती है. दिस इज वन कंप्लीट साइकिल. ओके, और ये साइकिल चलते रहते हैं, लेकिन विद टाइम डैम्पिंग और फ्रिक्शन की वजह से ये प्रेशर कम होते होते नॉर्मल हो जाते हैं. सो आई थिंक वी शुड स्टॉप हियर बिकॉज ओनली 5 minutes आर लेफ्ट. सो इफ यू हैव एनी क्वेश्चन यू आर वेलकम.
सर एक चीज पूछनी थी कि
इसका जो
पाइप
सर्कुलर होता है टाइम सेव करना है.
जी जी, हाँ जी, सॉरी मैं
सर ये वाल्व हम एकदम से क्लोज कर रहे हैं तो इसका पर्पस टाइम सेव करना है.
सॉरी, दोबारा रिपीट करेंगे सवाल अपना? जी जी,
चाह रहा हूँ कि हम वाल्व मतलब कर सकते हैं तो एकदम